Hello everyone, welcome back to CFD College. I'm Ashkan and this is the third tutorial of our ANSYS Fluent training course from beginner to advanced. In this tutorial, I'm going to show you how you can simulate flow over a rotating square cylinder. In previous tutorial, uh, we tried to simulate flow over a rotating circular cylinder. But in this tutorial, the cylinder has a square cross section, so the procedure is totally different. In previous tutorial, we used boundary condition to apply the rotation, but here we should use free motion or mesh motion. I will teach you mesh motion today, which is known as sliding mesh. It can be kind of dynamic mesh method. It is known as one of that, but it's a sliding mesh, or you can call it mesh motion. It's different from dynamic mesh. In this procedure, in this method, uh, the mesh, the cells, are not going to uh, regenerate regenerated again. We just use interfaces to separate two zones from each other, the stationary zone and the rotating zone, which rotates. And that's it. Simply, we can simulate this project. So before getting into it, please subscribe the channel. If you find these videos useful, please introduce us to your friends and like our videos. Okay, now we can see the domain. In this video, we are working in two-dimensional domain, as you can see here. This is our square cylinder, which rotates. This is our domain. Uh, the cylinder length is 4 centimeter. So this is 4 centimeter. You can see the domain. 50 centimeters is the distance between the cylinder and the inlet. And the distance from the cylinder to the outlet is 1.5 meters. And the cylinder is at the middle of the domain, so 0.5 meters up to top surface and 0.5 meters to lower boundary. This is our CFD domain. We should generate a good mesh, and in this tutorial I will generate a structured mesh. As you can see, the rotation speed is 5 rev per minute. Air velocity, air is the working fluid, enters the domain from right and moves towards left. Uh, the velocity of air is 0.5 meters per second. As I mentioned, working fluid is air, density is fixed, viscosity is fixed, and there is no heat transfer in this tutorial. So let's jump to ANSYS Workbench. And just you should know that in this uh, problem, in this simulation, since we want to use sliding mesh or mesh motion, we should do it in transient mode. So the simulation is not steady state, it's transient. Here is a fluid flow block. Let me go to Designmodeler. First, we need to generate CFD domain in XY plane. Go to sketching. First, this is, oops, let me undo it. Units, centimeters. Now it's far easier. Okay, this is the square. I have to give the dimensions, and since I want to, I want it, I want this square to be symmetrical regarding our x and y axis. I should use symmetry constraint. First the axis, then the edges. Again, that's good. Now 4 centimeters, 4 centimeters. It's good. And the domain, which is another rectangle, uh, the distance from the inlet, the distance from the outlet, it's vertical dimension. This one and this one, I think we are done. So it's 50 centimeters, 50 centimeters, 50 centimeters, and 150 centimeters. So this is the domain, but since we wanna work, uh, since we wanna use sliding mesh, we have to separate the zones. So we should have stationary zone and rotating zone. So to do that, I will generate another sketch. Let's see what we have. Go to concept, surface from a sketch, sketch one, frozen. This is our domain, but we have to break it into two sections, stationary and rotational. So sketch two, I should generate a cylinder around this square. That's it. And for the dimension, the diameter, it's up to you. But let's say 50. So 50 is perfect, I think. Or let's increase it to 80. Yeah, that's better. And now we can use face split to split these domain into two zones. So now, since I want to generate a structure mesh, I need some lines to decompose the domain. I will generate those lines. I will draw those lines in another sketch, sketch 3. First, I have to break it like this, and then, okay, let me add this dimension. This should be 50 because it's symmetric. And now other lines from here to this, from this point to this point. Oops. It's better to zoom in. Okay, now we can use face split. First for this, these are the lines. And next for this one, 2, 3, 4. Okay, as you can see, we have separated zones and it's perfect. So now I can close it, go to ANSYS machine. If you want to generate a structured mesh, you have to decompose your geometry every time. ANSYS machine, Fluent machine, ICM CFD, they can't do that for you. In ICM, you should create block and decompose your blocks. But if you want to use ANSYS machine, you have to do it when you generate the domain in Space Claim or Designmodeler. So now I will add Trace Machine because we want to have structure mesh. Then we should use edge sizings for these lines and for this one, this one, and this one. Oops, these two, and I should add these four. Okay, it's fine. And these lines, I think we should just use these. Yes. What else? What else? It's okay. So now let's create some names for these zones. This should be stationary and rotary. So let's say rotational rotary. And this is stationary zone. Okay, now this, and this. These are side. This is inlet. This is outlet. And now we have to let's say slice this zone because we want to use sliding mesh. Up to now, this mesh can be used if the cylinder, this square is fixed and it's not rotating. But if you wanna rotate uh, this zone, you have to have two different zones. See this? This is one zone. So this line is only one. But if we come back, we go back to Designmodeler and slice the zone, then we will have two different zones. How should we do that? We have some options. We can use Boolean. Oops. Where is it? Oh, or maybe we should use a slice. Yeah, we can do it. Let me use slice, slice by plane, slice of faces. No. Slice by surfaces. No, maybe slice of edge loop is better. So now this is one of the zones and this is another one. And now we have to click on this and do the split again. These are the lines. See now we have that configuration and here we have two different surface bodies. Uh, if you don't need to make them one part because we wanna use sliding mesh and we have to use interface for that. So instead of create names for these bodies in ANSYS machine, we can just rename the surface bodies here. So this is stationary, this is rotary. And now I should have duplicated this block because we needed that. If we wanted to simulate a fixed cylinder, we needed that domain, but I made a mistake. Okay, that's fine. So here, see, now we don't need these, so we can delete them. And under geometry, we have two surfaces, stationary and rotary. I always generate interfaces myself. So if you do this and in this section connections you had some contacts, you should delete them if you wanna go through my procedure. But you can leave it and make and let ANSYS machine generate interfaces. But I always generate them myself. So now we just do this again. These four lines. And okay, now we have two different zones. So you have to hide one and add these sizings. See, you can see the other lines. Or it's better to generate edge sizings for each separately. So this edge sizing includes 9 edges that are in stationary, as you can see. So I will create a new sizing for these lines. So again, if you wanna simulate a fixed square, you don't need to slice the geometry. You can just put or both. Also, you don't need two zones in that case. But if you wanna use frame motion, you should do the same. So this is my edge sizing and to create names, inlet, outlet, and sides. So four, these are square walls, and one, two, three, four. These are interfaces. So interface S. station. Oh, sorry, arc rotary. Then you should right click and invert visibility. This one. Now you can see the stationary domain. So these four should be interface S stationary. And let's check the sizings. Okay, now it's good. Show all bodies. Now let's deal with these sizings. Hard, we need biases, for example, 20, and the number of divisions 80. You should make sure that bias direction is correct. We don't need bias for these edges, and the number, I think 50 should be fine. So we should go to scale edge sizing 5 and do the same sizing as edge sizing number 2. Why? Because these interfaces should be matched with each other. So it's better to have the same sizing for the interfaces, not in this simulation, in every simulation. So, and what about this one? 50 and this one. Okay, for example, let's have 20. Let's generate the mesh and observe it. Okay, now we can examine the mesh. Here is fine. We have, it's not good. So we have to decrease the bias. For example, 10. Since the flow is turbulent, you have to check Y plus. You can see my video about checking the Y plus in CFD simulations in ANSYS. Okay, let's increase it a bit. And also this should be my 80. And we can use bias factor of, for example, 4. I should reverse the bias for this one. Now let's check the mesh. It's not bad. It's good, I think. We can continue with this mesh, sides, inlet, outlets, square walls, interface. And that's it. Just I have to update the mesh. You should see this check sign before opening Fluent. And let me save the project on desktop. Rotating square cylinder. Double precision, you will use 4 processes. So 4 pores for this simulation. The rotation speed is 5 RPM, air velocity is 0.5. Okay, now first let's calculate Reynolds number. let me do it here. Okay, we can do it manually. Uh, Velocity, density times hydraulic diameter divided by viscosity. 1361. The flow is turbulent. If you remember, I showed you different phases of the flow in, I think, yeah, in the first and also the second tutorial of this series. Okay, so we use k omega SST for this simulation. As I mentioned, the flow is transient because we want to have rotational square, rotating a square. Discuss, as you can see, the default is k omega SST. And that's it. There is no need to activate energy equation. Air density is okay. This is viscosity. And let's go to units. Angular velocity, use ref per minute. Then you should go to cell zones, cell zone conditions. Now you can see we have two different zones, rotary and stationary. There is no need to change anything regarding the stationary zone, but in rotary cell zone, you should active, right? This mesh motion should be activated. This is a sliding mesh, as I mentioned. So if you active this one, select mesh motion, this zone will rotate around this axis origin. So that's why I put the origin at the center of the square. Now I know the origin. And the rotational velocity is 5 RPM. There is no translational velocity in this work. And for boundary conditions, inlet is velocity inlet. The velocity is 0.5, if I'm not mistaken. Yes. And that's it. We have two interfaces here. We should match them in mesh interfaces. We have three walls. Oh, outlet is not wall. It's pressure. Oops, pressure outlet. And there is nothing to change. There is nothing to change. The pressure is atmospheric. The sides should be slip wall, so specified shear and 0. And the square walls should be no slip walls. And be careful that it's a stationary wall because it's relative to the adjacent cell zone. The cell zone, the adjacent cell zone for this wall is rotary. So rotary rotates, and these walls, square walls, will rotate with them. So click on right click on mesh interfaces, click on new, and select them and click on create. That's fine. Go to reference values from inlet. Where is inlet? Here it is. So the density, viscosity, the length is hydraulic diameter 0.04, and the area, let me check. Uh, did I make any mistake? No. Good. And area should be 0.04 because length multiplied by depth is equal to area. And that's it. Let's go to methods. Select auto select for the flux, and the discretization should be second order. It's fine. You can use second order implicit for transient formulation if you wanna have more precise and accurate simulation. Report definition, it's good to have some. For example, force report, drag force uh, of square walls. So this is drag coefficient. The vector is fine for me. And that's it, that's fine. Residuals, I reduce residuals to 10 to minus 4. And so now, uh, when you want to initialize the domain, CFD domain, you should be careful to select absolute when you have uh, sliding mesh, when you want to use sliding mesh. So click on absolute and read the compute from inlet, yes, x velocity, so it's fine. Click on initialize. Now let's okay. Let's create animation first. Solution animation, right click and click on new. Every, for example, 5 time steps. It's fine. And I need new object. So I will create 2 animations. No, 1 is fine. No, 2. The first object should be mesh. Let's see the mesh. And this is good. I just want you to see the rotation of the zone. So this is fine for me. Use active. And that's fine. And another one, contour. Contour of velocity, display. That's good. Let's zoom in and click on use active. Let's check this one. It's good. So after 5, oh, where is it? Okay, it's for mesh. Record after every 5 time steps. Fine. And for contour, that's the same. Okay, it's good. In transient simulations, since you wanna export data at different time steps and different time instances, you should always set autosave. For example, for me, every 25 time steps is fine, or every 20, let's say. It depends on you. Then go to run calculation and let's set time step size as 0.0011 millisecond. Yeah, I think it's good. And 100 time steps. Maximum iteration per time step 50 is fine for me. Now let's start simulation. You can see the simulation. Here you can see the mesh. This is drag coefficient. Here you can see velocity magnitude. If you see, you can realize that this zone is rotating. The residuals are fine. Yes, now I think the rotation of this square is clear for you. Time step is a bit small. I can increase it. Just after this 100 time steps, I will increase it. You should always check the residuals. And this is a perfect behavior of residuals in transient simulation. Okay, the first 100 time steps is done. Now I will change time step and increase it to 5 milliseconds. There's a jump in residuals, which is completely normal because we increase the time step. And now you can see the square cylinder is rotating. Wow. See the vortices? The separation, it's vortex shedding or vortex street, but when the cylinder, the square rotates, we will see more beautiful vortices. So this is how you should simulate uh, using sliding mesh method, sliding mesh technique. When you have a rotating object in your domain, whether it's like this, a simple cylinder, a simple square, a triangle, or even in compressors, turbines, pumps, where you have a rotating object, sliding mesh is the best way to simulate the project. As you can see here, I will increase the time step to 0.01. Now this is the mesh. It's really beautiful. Wow. So now uh, you can see the contour every 0.05 seconds because we defined that ANSYS Fluent store the contour picture every 5 time steps. So I think it's done and it's fine. Uh, I should run let it run for maybe 1 hour or less, and then after that we can see beautiful contour, lots of vortices. So the procedure is important. You should use sliding mesh. You should have different subzones, rotary zone, stationary zone, in order to use sliding mesh or mesh motion. And I think everything is straightforward. Uh, it's not difficult. Maybe, yeah, I think it's good to simulate uh, a rotating airfoil in one of the tutorials. So just let me know what you think about it. That's it. I can let it run forever. Uh, Nothing new will happen. And that's fine, I think, for today's session. I hope you enjoyed it. And if so, please subscribe the channel. Please introduce us to your friends. Give us a thumbs up. And you can follow me on LinkedIn. So I'm there. And that's it. Yeah. Thank you for watching this video. Thank you for your support. And until the next video, take care of yourselves and bye bye.